All right, we are going to be looking at this problem where we have a ladder represented in blue, and it is kind of leaning against this wall, and it has a weight of 10 pounds acting at the center G, and then we have an external force here, P. Okay, and we are given that the coefficient of static friction at A and B, so A and B right there, is 0.2. And our mission here is to find the smallest value of P where equilibrium is maintained. Equilibrium just meaning sum of forces, sum of moments is 0. Okay. So try this problem on your own. Come back, watch the solutions, learn from it, and then try it again on your own, right? But yeah, so the first thing I would do is assume that there is no friction. Draw a free body diagram, and then we have this kind of variable P. So I would find P, the value of P where the ladder is in equilibrium if there was no friction. So let's do that here. Okay, so there's my ladder. Right? It's kind of resting on this wall, so the wall can exert a force normal to that wall. So that way, it's resting at A, so the wall can exert a normal force like that. Okay, so draw my forces. I'm going to call this F sub B, F sub A, and we still have 10 pounds. We have P there. I'm not drawing any friction right now, okay? Assuming no friction right now. Now I want to find P such that this is in equilibrium. So let's we can do sum of the forces in the y direction, and we get Fa minus 10 pounds equal to 0. So we get Fa is just 10. All right, and then you can take a sum of the moments about G, where this kind of middle point is labeled G. So it's this force Fb times perpendicular distance there, which if you look at the problem is 7.5, so Fb times 7.5, it's positive from the right hand rule. And then this force Fa, which we've just found is 10, times this perpendicular distance, which is 4, it's negative from the right hand rule. So minus Fa times 4, and that's it. These forces don't cause a moment about G because their line of action goes through G. I can plug in 10 for Fa right there. If I solve for Fb, I get 5.33. And then the one equation I haven't used yet, sum of forces in the x direction, I get P minus Fb is equal to 0. Plug my value of Fb in there, and I get P is equal to 5.33. This is not my answer for the problem, okay? This is P such that the ladder is in equilibrium if there is no friction, okay? But in this problem, there is friction. So we can actually go lower than this, right? Maybe P can equal 4 pounds, and the ladder will still be in equilibrium because there's friction, right? You can also go above this value because there's friction. Maybe P could equal 6 pounds, right? This is P, where the ladder is in equilibrium if there is no friction. Because there's friction, we can go above and below this value and still maintain equilibrium. The problem is asking, how low can we go, right? The smallest value of P where equilibrium is maintained. So how low can P get and still maintain equilibrium? Okay, so we are venturing where P is less than this. All right, so in order to determine the directions of the frictional forces, we need to see which way the ladder wants to rotate. Okay, the P we're going to find is going to be lower than this, because again, we're seeing how low can we go below this. Okay, so we need to see what direction will the ladder rotate or move for the P that we're going to solve. So for P less than this. A simple p-value that's less than 5.33 is p equals 0. So if I draw the free body diagram, again, still assuming no friction, when p is equal to 0, this is what I get. Again, this is for no friction, just for a small value of p. So p is equal to 0 here. Okay, this is FB, FA. Pretty clearly, sum of forces in the x, I get FB equals to 0. From sum of forces in the y, I get this is equal to 10. If I take a moment about this point, this causes a clockwise moment, and there's nothing to counteract that. This force doesn't counteract it, because its magnitude is 0. So the ladder will rotate clockwise. Okay, so what we just did, we found P where the ladder is in equilibrium and there is no friction. Okay, the problem is asking how low can P actually go below that value when there is friction and still be in equilibrium. So we made P lower than that value, still assumed no friction, and determined which way will the ladder move / rotate. We found it will rotate clockwise. So when P is less than 5.33, the ladder wants to rotate clockwise, but friction will oppose that, and it will prevent it from rotating up until a point. And we're trying to find that point. Okay. So if I have my ladder here, and it rotates clockwise, what way is the frictional force up here at point B? Well, if I draw the wall here, this point right here will slide downwards. The ladder will slide down. So point B on the ladder will slide down relative to the wall. So the wall sees this end going down. The wall doesn't like that. It opposes motion. Friction opposes motion, remember. So the wall will exert a frictional force on the ladder upwards. How about this point? Well, the ladder's rotating clockwise, so this point is going to get kicked outwards. So if you're the wall, you're going to see this ladder end sliding to the left. You, the wall, don't like that. So you apply a frictional force to the right on the ladder. Frictional force opposes motion. This point wants to move left, so the frictional force is to the right. Okay, so when P is below 5.33 with friction, the ladder wants to rotate clockwise, but friction will oppose that and still keep the ladder in equilibrium, even when P is below 5.33. Okay? So let's draw a full free body diagram now that we know the direction of the frictional forces. And we did all this work to find the direction of frictional forces. Do not assume the direction, okay? Do not assume it is to the left and then be like, oh, I'll show after I solve stuff that it's actually to the right, okay? In general with friction, you can't do that, okay? You will get a very wrong answer if you don't, or if you do assume the direction, okay? There's a few special cases when you can. However, it's best just to look at the direction it wants to rotate or move, and then say, hey, friction opposes that, and then just draw it in the correct direction. Okay. So we have our normal forces there. We have our frictional forces at these ends. We still have a force P 10 downwards. Now we're looking for the smallest value of P that equilibrium is maintained. So when P is 5.33, these frictional values are 0. That's what we looked at before. So when P gets lower and lower, this frictional stuff, these forces are going to increase and increase, right, to oppose the ladder wanting to rotate clockwise. And so as P gets lower and lower, the frictional force gets higher and higher up until the point. Okay, now the frictional force can only get so high. Okay, and when the frictional force is at its maximum, that is when P is at its minimum. Because if you make P any lower, the ladder is going to want to rotate clockwise even more, so the frictional force will have to be higher, but you can't get higher than a certain point, like there's a max. Okay, so because we're looking at for the minimum value of P, we know that there will be the maximum value of friction at that minimum P. So the minimum value of static friction is coefficient of static friction times the normal force, in this case FB, because it's normal to the wall that is causing that friction. Similar for this frictional force, coefficient of static friction is FA. We are given the static friction coefficient. So we just get that. Again, I'll say it again. When P is 5.33, these frictional forces are 0. But as P gets lower and lower, the friction keeps increasing, increasing, increasing up until a certain point. When if P gets any lower, the frictional force would have to get even higher. But it can't. It is a max. Okay? So we're finding how low P can get, right? But the lowest P can get corresponds to when the frictional force is at its maximum. Because as P gets lower, the friction increases. All right? How many unknowns do we have? Well, we have FA. We still have FA right there, so that's still one unknown. We have FB, we have P. And we can write 3 equations. Sum of forces in the x, y, and the moment about the k-hat direction. And so we can solve all of these unknowns here. Okay, so if I take the sum of the moments about G is right there. I have this force times its perpendicular distance right there, which if you go back to the problem, 7.5 inches. FB, it's positive from the right-hand rule, and plus this frictional force times this perpendicular distance. Again, positive from the right-hand rule. So I get that. And then I have this force, it causes a negative moment. Its perpendicular distance is 4. And then similar for that frictional force at A, causes a positive moment from the right-hand rule. Set that all equal to 0, because we're looking for P when it's in equilibrium, so when the sum of moments is 0. I can simplify all this. I get that. So this is my moment equation. If I do sum of forces in the y direction, that's what I get. I can solve that equation for FA, and I get 10 minus 0.2 F sub B. So now that I have FA in terms of FB, I can plug that into, where is it? My moment equation right there. Okay, so after I plug in FA, this expression for FA, into my moment equation just has FB in it now. I can just straight up solve for FB. I get FB is 2.841 pounds. I plug FB into my sum of forces in the y direction equation to solve for FA. That's what I get for FA. Right? It's just solving a system of equations. That's all we're doing. Sum of forces in the x direction. My frictional force, plugging in the FA and FB values I found already. That's what I get. And I can solve, and I get P is 0.955 pounds. That's my final answer. That's how low we can go, right? If P was any lower than that, it's like if P was 0.8 pounds, then in order for it to be static or in equilibrium, the frictional forces would have to be even larger, right? But the frictional forces can't get larger than this. Okay, so that's why we used the maximum frictional force in our free body diagram, because we were finding the point where if P is any lower, the frictional force would have to be higher above the max, and that's not possible, right? So in other words, if P gets any lower, it's going to move, it's going to tip, it's going to accelerate. Okay, and that's exactly what the problem was asking for. Smallest value of P, where equilibrium is maintained. You bring P any lower, the frictional forces need to be higher. That can't happen, right? Beyond a certain point. And so it's going to accelerate. It's going to start moving. It's going to not be in equilibrium. Again, that's why we use this expression for the max static friction. So to recap, we assumed there was no friction. We found P, where the ladder is in equilibrium for no friction. And the problem is asking kind of how low we can go. How much lower than this can we get? Okay, so we made P lower than that value, still with no friction. And we found the ladder wants to rotate clockwise. So at the minimum value of P that we just solved, actually, the ladder wants to rotate clockwise, but friction opposes that. So we looked at kind of how the ladder will move if it rotates clockwise, and we drew the frictional forces to oppose that motion. So we drew a free body diagram with friction, for reasons I talked about a million times already. We used the frictional force as the max static friction force. Okay, and then we just wrote out a sum of moments, sum of forces equations, solved that system to get our final answer here.